All right, so we are in Unit 1, Lesson 4, Graphs of Common Functions. There were a lot of questions about, or a few questions rather, on the piecewise function. How did I know it should take that shape? Well, moving forward, we're going to talk about 6 different root functions. You're going to need to recognize them in their equations and be able to graph them without a calculator. All right, so we're going old school with this. The first thing we need to be able to do is to look at an actual equation and determine what its shape should be. So as a quick review, I have these 4 equations that are up here. Can you tell me what number 1 would look like when we graphed it? Anyone? 1, 2, 3, 4, 5, 6. From Allie. Right?
Oh, yeah. It looks like a straight line.
How do you know?
Because it's a normal function.
What is it in here that tells you to graph a line? You're right.
The slope.
Okay, so there's a slope. What else?
The y-intercept.
Okay, this is a y-intercept. Anything else? Okay, go ahead. All right, the power of x is 1 and the power of y is 1. Okay, that's the indicator that you have a linear equation. Polynomial degree 1 is another way to say that. If I look over at number 2, what should the general shape be of number 2? Think about it. And then I'm going to ask you, how do you know? Go ahead in the back.
It's a
Parabola.
parabola.
How do you know?
Because there's 3 terms. But the degree, the highest degree is 2, which is
Exactly. The highest degree is 2 of the x variable, which is our input variable. It is in the standard quadratic form, which is ax squared plus bx plus c. That is true. And the highest power of y is 1. If you move down to number 3, what shape do I have there? What do you think? Yes. Okay, and how do you know it's a parabola? Because of x squared and a y to the first power. Now, most of the time we don't look at y, but it's important because now when we look at number 4, does anybody know what shape number 4 is? What do you think? Yes. Close.
Oh, wait.
It's not a circle, but I know what your thought process is. Why were you going to say it's a circle? Correct. So the first thought process, did you do conics in algebra at all?
We
Touched on it?
touched on it, but we didn't go very into it because we knew it existed, but we didn't really go into solve it or whatever.
Okay, so if I take a look at number 4, I have an x squared and I have a y squared. That does indicate a circular shape. However, because I have a coefficient on one but not the other, that's what makes it an ellipse. Or like an oval, kind of a general term. Okay? Circles would have the same exact coefficient. So not only did you identify the powers, but we also have to look at the number that's in front. Changes it. Right? You didn't do a lot with that, I understand. However, we do have to go through and analyze the equations to figure out what the shape should look like. So here are the 6 functions you are responsible for. For tomorrow, you need to prepare for a general quiz where you have to recreate the 6 of these, writing the function, plotting the key points, and drawing them. Not shifting, not flipping, just this slide. So put a note in your notes that you need to prepare for it's a knowledge check of the 6 graphs. We can't move forward if you don't have the basic graphs memorized. So let's talk about what these were. The first one is y is equal to c. Okay. In this case, I believe you have y is equal to 4, correct? Y is equal to 4. That is the constant function. It is a horizontal line. What would you tell me the domain is? How far left, how far right? Good, shout it out and we can get through it quickly. How about range? What's the only y value? 4. So we're going to learn a new symbol today. I believe they're called braces. They're those squiggly looking brackets, like this. In math, when you have a solution that is a single value, not an interval, you're going to use braces. function is the identity function. Y is equal to x. Okay? If you want, you can say 1 over 1x plus 0. That's going to be in the y equals mx plus b form, which most of you are very familiar with. The key point here is the fact that this 0, 0, and my slope up 1 over 1 is going to be there. What would you tell me the domain and range are? They are the same. Negative infinity to infinity, negative infinity to infinity. That is not a default. You're answering the question. How far left? How far right? How far south? How far north? Absolute value we talked about in the prerequisite unit. Absolute value is centered at 0, 0. That's one key point. The other key points are going to be go to the right one, up 1, left 1, up 1, and then you can make the V shape. Those are the three key points that you need to know for absolute value. What would you tell me the domain is? How far left and right? Yeah, negative infinity to infinity. And what about my range? How far south? 0. Now, I'm going to write something here. Is 0 as a y value, because range is y, would that be in a table in your calculator? If you had your calculator here, would you be able to scroll into the table and see y as 0? Like, would 0, 0 be in the calculator? Yes. Because of that, the range, this is a bracket. Okay, we're not talking about increasing and decreasing. We're talking about domain and range, inclusive or boundary. All right, let's go to square roots. This is the one, AJ, you had asked me about this one. Square root starts out at 0, 0 also, key point, over 1, up 1, and then it swooshes. So it's basically over 1, up 1, and then it just swooshes out to the side. That's where you get that curve from. Okay? I actually refer to it fondly as the swoosh graph. Who doesn't need another nickname to remember? My domain, how far left? Goes all the way to 0 with a bracket. And then all the way to infinity because it grows out to the right. What about range? How far south? 0. It grows all the way to infinity also. Now, interestingly, y equals x squared is the parabola shape we've talked about. It's referred to also as the squaring function. 0, 0 is a key point. Over 1, up 1. Over 1, up 1 is also a key point. The squaring function has the exact same key points as the absolute value function. The difference is in the shape that you draw. So, over 1, up 1. Over 1, up 1. When I'm drawing absolute value, they are stick straight. When I'm drawing the squaring function, they are smooth curves. These are not the same shape. What's my domain, left and right? And range? 0 to infinity. Good, we're able to see these. The last one that you are responsible to know and work with is your cubing function. Your cubing function also starts at 0, 0. You are going to go right 1, up 1. And you're going to go left 1, down 1. So it kind of looks like the identity function. However, it's comprised of a curve up and a curve down. That is going to be your cube function. These are the 6 you're responsible to know. Quickly, domain, how far left and right? Negative infinity to infinity. Range? Negative infinity to infinity. Done. So, these are the keys to the kingdom. If you ask a math teacher, what does this graph look like? This is what we're doing. All right, there's probably 3 or 4 other graphs that we have memorized also, and then when we get into trig, there'll be 3 more. But this is the heart and soul of all the graphing. This is how people did it before they had a graphing calculator. Any questions? Now, here's what I'm going to tell you. This is where the road, what is it? feet hit the pavement, the road hits the pavement. I don't know, some vernacular or something. When you look at what we're about to do, okay? Number one, you are not putting it in your graphing calculator. This next test will have a portion on it that is in no calculator section. Okay, that's the first key piece. Second thing is that we are not using a table method. Okay? We are talking about families of functions where, let's say, just randomly, this is my function at random. This is what it looks like. It's a cone. We're going to move the cone up, down, left, right, flip it upside down, stretch it out, make it taller, make it wider. The cone stays the same. We're not plotting points. We're not doing anything. We're going to go off of these key points. Got it? We're not calculating points. We're taking one shape that we know and memorize, and we're moving it in the coordinate plane based on the function notation that we're given. You're learning the rules of functions. That's the big idea with what we're about to do. So another way of saying that is the transformation of graphs. Wow, it sounds so formal. Take a look. The transformations of graphs. The first notation that we're going to talk about, if you want to get a highlighter, you're welcome to do that. We have a plus C or a minus C at the end. It is a number by itself. Now, this can be a little bit misleading. Okay? Here's the reason why. Like right here, I could have this is equal to 5 plus x squared. It still means it's a vertical shift. Okay, the order isn't, it's the fact that the 5 is by itself. When I read through my equation, I need to read the function and say, oh wait, I have x squared, that makes it a parabola. The plus 5 at the end says take the key point 0, 0 and move it up 5. Okay, so when we're talking about numbers at the end, it's going to follow the sign. Take a look. Here's my xy axis. Plus 5 from my x squared means I'm going to move up 1, 2, 3, 4, 5, and I'm going to make my new vertex. From that point, pretend like it's the origin, you're going to count right 1, up 1, left 1, up 1, and draw your curve, and you are done. That's it. That's what we mean by shifting transformations in the plane. Transformation vertical follows the sign. Plus 5 is up. What am I going to do with my parabola here? I'm going to move it down 5. Okay? So if I take a look at this one, I'm going to go down 1, 2, 3, 4, 5, down here. Right 1, up 1, left 1, up 1, and I'm going to draw my curves. Okay? I'm sure you already know this. We're going to start small, look at each different transformation, then we're going to put them all together. That's when it gets a little bit tricky. All right, let's talk about horizontal translations. Horizontal translations are talked about moving, taking your graph, whatever it is, moving it left, moving it right. I did that opposite with my hands, but the reason I did it opposite is because whatever is inside of the grouping symbol, I always want to use the opposite. So if this is take x, it says plus 2. X is along this way. I'm actually going to move it left 2. And if this says minus 5, that means I'm going to move it right 5. What is it that I'm moving? It's always that key initial point. Usually it's at 0, 0. That's where I'm going to move it within the coordinate plane. So for my first one, I'll draw these two separately this time. For my first one, I'm going to move it to the left 2. 1, 2. Put my new key point. And then say to myself, what does this graph look like? Oh wait, it's x cubed. So I'm going to go right 1, up 1. Left 1, down 1, and draw my little super swoops. Swoopy. X minus 5 says to move the graph right 5. 1, 2, 3, 4, 5, key point, up one, right one, up one, left one, down one, swoopy, swoopy. Shifting the graph left and right. Okay. First type of reflection. We're going to be taking graphs. So maybe I have a graph, this is my cone that normally sits like this. Maybe now I'm going to be turning it downward. Okay? That's known as an x-axis reflection. And this is where understanding function notation, which I know some of you are still struggling with, please come see me if that's the case, becomes important. Look at your table. X is the first column, f of x is the second column. F of x is short for y. So if I put a negative out front, doesn't that translate to I want negative y? I'm taking a point from whatever it is, positive y, down to negative y. That's the x-axis reflection. Right? Short term for me, I call that the garage door flip. Garage door. The other one is going to be the front door flip. Left and right. Nobody has a front door that opens like this. No. Okay? So we're going to talk about the garage door flip top to bottom. Here's our example of that. I have the x squared function, so I'm looking at that swooshy looking one, the swoosh, that's now going to be a reflection where I take the positive y's and make them negative. Right? This is what it looks like if I was doing the graphing calculator. So I still have 0, 0 as my key point, but rather than going right one, up one, I go right one, down one, and then I draw my swoosh. A y-axis reflection, notice the negative is taking x. So now I have x, or then I have f of negative x, which means that I'm taking the graph from positive x to negative x. I'm swooshing it over, switching it this way. So if I look at that with my square root, instead of going right one, up one, I go left one, up one, and swoosh back to the left. All right, 6A. You do not have this one in your notes, do you? Do you have this one? No. All right. I added this one because there's a problem in the homework, and everybody was getting it wrong, and everybody always asked about it. So I put one in similar to it just to kind of address it from the beginning. If you take a look at this function that I have here, notice I have a negative x. Okay? What this is considered, by the way, is in grouping symbols. So underneath square root, that's an example of a grouping symbol. In between absolute value, this is considered a grouping symbol. So that's going to signify a left and right shift. Okay? Inside of your x cubed, that's going to be a left and right shift, all the same idea. Whenever you see a negative x inside of a grouping symbol, we always want to make it positive. So in this case, I want to rewrite this as this. You have to rewrite it. So you might want to write this down somewhere so you don't get this incorrect. You're going to rewrite it because now you can see I'm going to have this left-right shift of the square root, but then I'm also going to move it not to the right, but I'm going to move it to the left. I'm getting my graphing information from the transformed or different function. So when I go to graph these two, I'm going to take my key point, I'm going to move it left 3, 1, 2, 3, which is here. Instead of going over 1, up 1, I'm going to go left 1, up 1, and come out this way. Now, this is a tricky thing, but there's a negative out front. If I wanted the vertical flip, it would be in front of the root. Vertical flip is all the way out front, not inside of near the grouping symbols. questions on that? Anybody? Yes.
So that negative sign, like where do we apply it? Do we just disregard it then?
This one here?
Yeah.
That's what gave you the flip to the left instead of to the right.
Oh.
Okay, so this tells you to go left. This tells you to do the left-right flip. Or what they call the y-axis reflection. Questions on that? All right, non-rigid transformations. All right, so we have a little problem. Little problem, big problem, huge problem. Okay, C is going to be a coefficient. C is a coefficient, hence the letter C, the choice. Okay? If C is greater than 1, it's going to make it taller. So we have two examples that we have at the bottom. Take a look. You have a 4 and you have a 1/3. All right, now, if I told you, which is very true, that I'm 4 times as big as I was before I had a baby, what do you think? What do you think of? What happened to me if I'm 4 times as big? I'm bigger, right? 4 times as big? Yes? Are you with me? Okay, here's the problem. When you multiply by 4, you think bigger this way because that's like the vernacular we use. That's how we talk. Like, oh, you're 4 times as big. The problem is in math, it's not like that. When I multiply by 4, I get taller. Here's the reason why. I'm taking 4 times x to get y. Y is the height part of it. So a 4 out front is called a stretch. That's when we have C greater than 1. It makes the graph taller. Whereas if I multiply by 1/3, it makes it fatter. Trust me, I'd like to be 1/3 my size. Maybe not 1/3, maybe 2/3. But still, it doesn't, you have to like switch in your brain, like commit that to memory, that 1/3 doesn't mean squatter or smaller. It doesn't mean thinner. It's the opposite relationship of what you think because of how the math works. So if we take a look at the square root, the absolute value, multiplying by 4 still starts me at 0, 0. But think of this for the first point only to the left and right with the key points as slope. I want to go 4 times as big. What is slope a relationship of? Rise over run. So I'm going to go up 4, 1, 2, 3, 4, 1, 2, 3, 4 over 1. Notice how my graph got steeper when I graphed it? And then with the 1/3, same thing. I start at 0, 0, but I go up 1 over 3, up 1 over 3. Now it got wider. Okay? So the 4 is steeper, the 1/3 is going to be wider. All right, by the end of the day today, the last 4 examples will be in the Google Classroom that you can go in and get them. They won't be a paper. I'll be talking and explaining them. And then you have assignment number 9 for homework. Okay? So your work is to watch the video, fill in the notes, and then do the assignment. Got it? Okay, so I'll make sure we have the notes done, finished. I wanted to go through the notation and spend a lot of time on that. I was not planning on being in a meeting this morning, or I would have been here another 15, 20 minutes. I couldn't miss it. Okie dokie. If you're planning ahead, we're looking at a test on the 20th, next week. You're planning ahead. Okay, review day Tuesday, test on Wednesday. I believe it's the 20th. Is that right? September 20th, yes. For the second second part of the lesson, we're going to examine functions to determine how they shift and flip, and then we are also going to take more complex functions and graph them using multiple transformations and stretches, and etc. So if we look at part A, describe and the graph, all we're doing is looking at the notation. So for this first part, we're going to look at the -7, say that that is a constant at the end, which indicates a vertical shift. If you remember, vertical shifts always follow with the sign. So -7 would mean that we are going to shift the graph or a parabola down 7 from its original position. In part B, we've got two things to consider. We've got the +5 and we have the 3 out front. Right? The +5 looks like it's at the end. However, as we discussed in class, this is actually understood grouping symbols. So that +5 is going to be an indication of a left-right shift. In this case, it's going to be shifting to the right. When we extract information about graphing from inside of parentheses, we always do the opposite. The 3 in the front tells you that the graph is going to get taller. Remember, yes, it's 3 times, but it's making y bigger, not x. So possible ways we could answer this would say that we would shift the graph left 5 and a stretch of 3. In part C, we're dealing with absolute value, and we actually have 4 different things happening based on the notation in the function. Okay? The first thing that we have is that the v is going to be upside down because there's a negative out front. The second thing is that you're going to have a right shift. Again, inside of parentheses is understood. Inside of absolute value are understood parentheses. So that's going to be a shift of right 2. +1 at the end is a vertical shift, following the sign. And then the 4 in the front, just like the last example, is a stretch. So the V goes from a standard shape to a much narrower shape, pointed in a downward direction. We could answer this by saying reflection on the x-axis, stretch of 4, shift right 2, shift up 1. Now, we're going to write the equation for each graph. The reason why these examples were given to you in the graphing calculator is that in your homework, you're going to have to plug in the examples and look at the picture. So I wanted to mimic that when we went over our notes. If you take a look at our key point, which is right here, you can assume these are always 1 to 1. And we can say, look, I have the f of x function being the square root function. It is shifted right 2, down 3. And if I go up 1, over 1, even though it's stretched out a little bit based on the scale, I still have the standard square root function. So notice I went up 1, and I went right 1 as well, which means it's a standard square root. Writing my function then, I'm going to say f of x equals, on a test or quiz, if you forget that and just write the rest of it, you will lose points. You are asked to write an equation. I used my square root function. Notice the x minus 2, I shifted it right 2, which means I need a negative 2 underneath the root, and then I shifted it down 3, which follows the sign minus 3. On the right, we have the same similar situation. We've got absolute value opening downward here at 1, 2, 3, 4. I would go left 1, down 1, right 1, down 1, which means it's a standard absolute value graph. There's no stretching or reshaping of the graph itself. Translated to notation, f of x is equal to the negative, which opens down, x minus 1, because I shifted it right 1, we use the opposite, plus 4 matches the vertical shift, up 4. Draw the graph for each equation. Step number 1, identify the home equation. Find the new key point. In many graphs, we refer to them as like the vertex or starting point. Plot the other points associated where we count off of the original point. Again, we are not making tables. We're doing this off of what we know as the home graph points. So I'm going to use x cubed as my original function. I'm going to shift it right 1, up 2. Right 1, up 2 gives me this key vertex or center of the graph. right one, up two, opposite, following the sign. Right one, up one, left one, down one. Those are my 3 key points, and then I can sketch in the graph to have the correct shape. So again, this is my heart and soul, the basic starting point of my graph. In number 2, I want to recognize I should have the swoosh of square root, shifted left 1, up 4, but the square root function isn't going to curve up. The negative is going to make it curve downward. So I go left 1, up 4. Here's my key starting point. Normally I would go right 1, up 1, but the negative out front causes that flip down, and then I can draw the sketch of my graph swooshing downward from the starting point. Three and 4. Number 3 is a little bit tricky because, again, we have the 1/2 to be aware of. That 1/2 takes my V shape and it doesn't make it smaller, it actually makes it wider. So for 1 point away and only 1 point to the left and right, we're going to think of the 1/2 as slope. We can't apply it in the parabola equations, but we can use that here with absolute value for at least the first point. So if I come over here and I draw my graph, I'm going to go right 2, down 3, right 2, down 3. Here's my key starting point. I normally would go right 1, up 1, but my slope says rise of 1 over 2, rise of 1 over 2. Notice it made my my absolute value flatter. And then I can draw in my lines with my arrowheads on the end. Now, in example 4, we need to be careful because we have y equals, but the ordering of the rest of the expression is different. Okay? Step number 1 would probably be to rewrite this. Okay? This is, in fact, the +2, a vertical shift. It is not a scrunching or stretching of the graph at all. From here, I can recognize it as a parabola. It opens downward. The vertex would be left 1, up 2. I don't have any stretching, so right 1, down 1, left 1, down 1, and then I can draw my parabola shape in a downward direction.